Okay. So we'll have a little bit of review of linear dynamical systems. In the linear system, we have the input. We usually call the input U. But we have U as our velocity field. I don't know what symbol do you like. I will just keep calling it U, and hopefully you will be able to differentiate. So this is your dynamical system. Usually we say G of S, right? Where S is the Laplace variable. Again, we have our own S, so I'll call just the Laplace variable P. And we have here the output Y of T. So one particular input is the step input, and the response due to that is the step response. So for this guy, the input is simply unity, but for positive time. So U of P in the Laplace domain, anybody remembers? The Laplace of 1 is what?
1 over S.
1 over S, so 1 over P. Okay. So the output, if you want to compute the output, we're gonna multiply the input in the Laplace by the transfer function in the Laplace. So this is G of P times 1 of P. This is your output in the Laplace domain. We do Laplace inverse for this guy to get our step response. Okay, Y step. Okay. And it may look like this. So this is Y, not G. If this is time and this is Y S of T, it may look for some class of systems, it may look like this. Okay. When you look at the step response, there are things that you can get out of this figure. First of all, the steady state limit here. This guy. So Y steady state is simply the limit as t goes to infinity of Y S of T, right? This is for a unit step. Actually, we call this the DC gain of the transfer function. Can you get this thing, this number from the transfer function, which is a function of P? Anybody remembers how to get this value? Put S equals what? Or P equals what? 0. Okay. So put 0 in your transfer function, you get the DC gain. The DC gain is very important. Why? Because if the DC gain of your system is 10, you give it a unit step, you will get 10 steady state out. So for a DC motor, for example, if the DC gain is whatever, 1000, then you give it 1 volt input, steady state step input, you get steady state 1000 RPM, okay? Something like this. So the DC gain is something very important to know about your system. For a closed loop system, well designed, it should be unity, meaning 0 steady state error, right? So this is the DC gain. How we get it? Just put S equals 0 in the transfer function, or P equals 0. Another thing is something called the high frequency gain, but to understand it better, I will go over there to the other very distinct response, which we call the frequency response. We talked before about the frequency response concept, but I'll do it again. So actually the input now is not unity, it's not a unit step, but it's maybe A cosine omega t. Then the output, and this is the steady state output, so we ignore the transient. Unlike here, we focus on the transient. We ignore the transient. The steady state is also sinusoidal, so it's a cosine omega t, the same frequency. But there are two different things. First, it's no longer the same amplitude. I'll call this B. So it's no longer the same amplitude A, and there is lag, there is phase shift. Okay? So if you're given here, this is your input, for example, t, and u of t, it's cosine, so it's going like this, and so and so. Your output, y as a function of time. Again, there is some transient that we ignore, okay? And after that, it will develop a sinusoidal pattern. This is its amplitude, and if you get the distance between the zero crossing, or between the two peaks, or between the two troughs, between any two similar points of the input and the output, this is the T lag, the time lag between them, which is, the T lag is simply this phase shift divided by omega. Okay? So the phase shift is simply a lag. Okay? Okay, so you give an input sinusoidal, you get an output, and there are two things, B and phi, right? For any A cosine omega t, give it to any linear system, you will get that. So it's obvious that B and phi, these three things, have something to do with the transfer function. If you give A cosine omega t to a car, to a submarine, to an airplane, or to an oven, the response will be different in terms of B and phi. So B and phi have something to do with the transfer function. Simply, B is the magnitude of your transfer function when you substitute every p by I omega. So your transfer function is a function of p, Laplace. Remove every p with I omega, so now it's complex, and it's function of omega. So for a given frequency, for a given omega, it's a complex number, the magnitude of which is the gain of the transfer function. The magnitude of which is the number that multiplies the amplitude of the input to get the amplitude of the output. And the phase of which, the angle of which, is your phase. Okay? So it seems, because these are the one that differentiate a system from another, we need to have a deeper look on them. And this is precisely the Boudy plot. So the frequency response, it's simply a function of omega by replacing each p in our transfer function by I omega. So it's a complex number, has a magnitude and phase. The magnitude amplifies the amplitude input, and the phase makes some lag. And it turns out that this magnification and lag, they depend on frequency. So this is frequency, this is the magnitude of it. Typically it's something like this. And the phase typically is something like that. This is the phase. Fine. Well, how to get the DC gain from the frequency response? Here is the DC gain, right, at omega. DC gain by definition, it's DC, it's steady state, so the omega equals 0. So this guy at omega equals 0, this is the DC gain, okay? And typically, for a well-established, for a well-designed system, at this guy, at the DC, we have zero phase. Zero phase meaning no lag, right? Meaning no dynamics. It's an algebraic relation. You just get the input multiplied by the DC gain, which makes sense for a steady response, If you have any question, please stop me. This, like I said, this is just review of linear dynamical systems. It's your 170 in here, the undergraduate controls course. but we need these concepts for our anesthesia system. So just a few minutes later, we'll replace this guy by our aerodynamic transfer function. Okay, so we learned from the step input, from the step response. The DC gain is something important to know. Here is how I can know from the step response, the time response. And here is how can I get it from the transfer function, just put P equals 0. And here's how can I get it from the frequency response. Okay, the three things. Step input, transfer function, frequency response. Step response, I'm sorry. Step response, transfer function, and frequency response. The other limit, so this is at infinite time and 0 frequency. The other limit is the other way around. So this is the DC gain, this will be the high frequency gain. So the limit as omega goes to 0, this is K high frequency. The high frequency gain. Okay? And what's the high frequency gain? Think about it. What's this omega? Omega is the speed of your input, how fast your input changes to the system. So you're changing your input infinitely fast. Typically, for a mechanical system, for a system that we deal with in our length and time scale, it will not feel anything, right? You're giving it an input that is infinitely fast varying, okay? It will not feel anything. If you're driving your car and you're oscillating your gas pedal infinitely fast, the car will not feel anything. Your speed will not change. If you're flying an airplane and you oscillate the elevator infinitely fast, the airplane will not feel anything, right? It will not feel anything. So typically, this curve goes to 0 for large omega, okay? But anyway, I mean, theoretically, there is some value. So the high frequency gain is the limit as omega goes to infinity, right, of this magnitude. And this value, this saturates. So this guy goes to 0 and this guy goes to also a constant value. If you remember, this constant value is simply how much the degree of the numerator and denominator of the transfer function. So the degree of the denominator minus the degree of the numerator, this difference multiplied by 90 degrees. So the difference between denominator and numerator, if the denominator is higher than the numerator by 1, then this will be 90 degrees. If it's higher by 2, then it will be 180 degrees and so on and so on. Okay? Okay, how can I get, so we learned how we get the DC gain from the three, the triplet, the step response, frequency response, and transfer function. What about the high frequency gain? So here is how can we get it from the frequency response. How can I get it from the transfer function? How can I get it from the transfer function? What's the difference between the transfer function and the frequency response? It's simply put P equals I omega, right? So if omega is infinite, P is infinite too. So also the high frequency gain is the limit as P goes to infinity of your transfer function, okay? And when you put it this way, you immediately realize that if the denominator of the transfer function, if the denominator is of higher degree than the numerator, then this guy will go to 0, right? So this would be 0 if the degree of the denominator is larger than, strictly larger than the degree of the numerator. So I will do like this, like it's not equal, okay? If it's equal, if dd equals to dn, the degree are the same, then the high frequency gain will be some number, not 0, okay? Typically the ratio between the coefficients of the same power, of the largest power. Okay, so this is if the degree of the denominator is larger, this guy is 0. If the degree of the denominator is the same, it's finite. Can the degree of the denominator be less than the degree of the denominator? So this is a possibility, this is a possibility. The remaining possibility is that the degree of the denominator is less than the degree of the numerator of the transfer function. Can this happen or not? It cannot happen for causality. For a causal system, meaning that the current output depends only on the current input and the past history. So these two must be satisfied, either. But the other way around, it cannot happen. The other way around implies that the current output will depend on the future inputs. This is not a causal system, okay? So the remaining possibility is not even a possibility. So I'll give you here an example. So if you have maybe p squared plus 3p plus 2 over p squared plus 4p plus 1. From here, what's the DC gain? It's very easy. What's the DC gain? What's the DC gain? 1. The DC gain is 2. The DC gain put p equals 0, SA equals 0. What's the high frequency gain? 1. Yes, this is 1. So I'll make this 4 just to, So the high frequency gain, put p equals infinity. So, you divide by the largest power, p squared, and typically the division of the coefficients of the largest power. So you can immediately see here, if this guy is not there, if the degree is not equal, so this is less than that, then the high frequency gain is 0, right? Okay, so the high frequency gain, which is the magnification of the input amplitude for very, very high frequency. Typically it's 0. The transfer function doesn't do any magnification. It just multiplies by 0 for a realistic system. But anyway, theoretically speaking, you get it from the frequency response. Look at very high frequency. This is the high frequency gain. From the transfer function, put p equals infinity. How can we get it from the step response? Any idea?
The initial value?
Exactly. So, we said infinite time is 0p or 0 omega. So now infinite omega is 0t, is 0 time. Okay? So this guy, the initial value, because when you give a step input subject to 0 initial conditions, this guy has to start from 0. But if it immediately picks up something, then this is due to the high frequency gain, right? It immediately gets it. So this is the high frequency gain. It's an infinite frequency, right? So this is the K high frequency.